So, continuing with explorations in momentum, this is the next video after thinking about momentum and impulse explorations. I'd like to introduce you to impulse, and so hopefully it arises sort of naturally in what unfolds next when I discuss collisions. Yeah, and we are headed towards ultimately a big idea. It's so big that everybody refers to it as a law. It's called the law for the conservation of momentum. Yeah, this is a big deal. All right, so the way I'm going to sort of unfold and talk about impulse is I'd like to talk about collisions, but before I talk about collisions, I'm going to revisit this version of Newton's second law really quick. So this is the net force on m is the time rate of change of the momentum of that object. I refer to it as m, but m stands for its inertia or mass. So let me rewrite that again. So F net on m is a vector, and it is the time rate of change of the momentum. The reason that I'm putting this word collision up here is I want to study the case of, for example, here comes an object on its way in, and here is another object. Let's say that this could be the scenario that B and A are on a collision course. So this, let's say, is the picture before they have their little crash, and we could say that they're aluminum foil balls or something like that. Aluminum foil balls. So you just take two lumps of aluminum foil and you crush them up, and so you got these two balls and you throw them at each other. And after the collision, they may look like this instead. So here goes A. It's got sort of a flat back here, and here goes B. B got crushed a little bit harder, but the mass of A is the same as it was before. The mass of B is the same as it was before, and they just are deformed a little bit, and they are now headed away from each other instead, right? So they're headed away because they bounced apart. Now, if I pay attention only to the object B, B was headed towards the left, and now after something happens, it's now headed towards the right. And the only way that I can take this velocity towards the left and make it into a velocity towards the right instead is to have used a force on B. So there must have been a non-zero net force on B towards the right. If I look at A all by itself, here comes A towards the right, but something happens to it and now it heads towards the left, and the direction of net force that does that to A is a force towards the left. And if you think about it, the reason that B turned around and went back is because A forced on B, and the reason that A turned around and went back is because B forced on A. And it starts to sound very Newton's third law, right? So you can have action-reaction pairs going on in here. But anyways, B has one momentum, incoming momentum headed leftward, and now a little bit of time later it's got one headed rightward, and the reason is because there must have been a force on B. Same story for A. Yeah, so you can kind of see how everything is connected. But let's go and study very simple starting point. So here's the starting point that I'd like to start thinking and exploring in. And here's what we're going to do. So this statement right here is really interesting. There is this equal sign, claims that the thing on the left has the same value as the thing on the right. But what's interesting is it's on the instant. And what I mean by that is the instant that the value of the net force on m is whatever value it is, on that very instant, at the same time, the time rate of change of the time-dependent momentum has the very same value. This is instantaneously true at the same time. Not at different times, but the same time. So this is begging me, honestly, to think in terms of integrals. So let me show you what I might do. So I'll take this equal sign, and I'm going to multiply both sides by dt, a small time change. So this is f net on m. So I just multiply by dt, and if I do it on the left, in order to keep the equal sign, I have to do it on the right. So d by dt of p of t, and then multiply by dt. And then I'm going to imagine that I've chosen some dt's that match these dt's. So these are meant to be the same limit as a delta t heads towards 0. It's the calculus limit on our real number line. So now I can do a summation. So actually, sorry, let me not do that yet. So forgive me, I'm scrubbing out the integral symbol. So I've got f dt and d by dt of p dt. And so if I imagine this dt and that dt to have the same amount of time associated with them, they will cancel because they're not 0, so you can multiply and divide by the same number, albeit it's small. So this is a dp at t, right? It's a leftover, very, very small change in momentum. This is a small change in p that's centered around the time t. But we're imagining the momentum is changing because the motion of this object is changing in time. So over here, though, this is f of t dt, like this. So this is the multiplication of some number of newtons at some instant in time times a small time duration, or a small duration of a moment. And the idea is, if this force gets to act for that amount of time, then, this net force acting on m, acting for this small amount of time, will cause or affect, it affects this small change in p. So the small change in momentum is because of f net happening for a small time. Right here is the gist of the impulse momentum theorem. And that's what I'm going to put on the next page. So I'm going to rewrite this line right here. So the net force on m is equal to, or times a small amount of time, dt, is equal to a small change in the momentum of the object whose mass is m, right? And I'm going to identify that this weird construction on the left-hand side is, right, it's got to be a calculus thing. It's a d, and then it depends on the textbook you look at, but in the textbook that these for the course that these videos are for, the symbol is capital J. So dj is equal to the net force times dt. So these are both infinitesimal calculus quantities that happen to be vectors. In SI units, this thing called J is Newton's seconds. So it's force and time multiplied by each other. So the SI units of this thing called dj is force times time. And this thing is called the impulse. And the impulse momentum theorem is written this way. The change in momentum of an object is equal to the impulse delivered by the net force. So the change in momentum of an object is equal to the impulse delivered by the net force. The net force delivers the impulse F net dt, and that is dp. And this thing we are calling dj, like this. So this is the impulse. It's a force happening over a time duration. And if you have an impulse, then you will have a change in momentum. So yeah, so I'm gonna write one more line. Maybe I should write it right here towards the right. So let's be really careful. This really is the impulse delivered by the net force. It's only the net force that results in the change in the momentum. Although you can define the impulse of any particular force, it's just equal to the value of that force times the small time over which whatever force it is acts. But if you want to talk about change in momentum, then it's equal to the impulse delivered by the net force in particular. So you really ought to match up the net impulse is the result of adding up all of the small impulses, which looks like this: the integral of f net dt from, say, t1 up to t2. It's equal to the integral of small changes in the momentum that go from, say, some starting value of momentum p1 and finish at a finishing value p2, which is p2 minus p1. That's just how you do the integral of the infinitesimal alone. And this is delta p. It's the momentum after the impulse and the momentum before the impulse. And the impulse itself is the net force on the object multiplied by small increments of time, and you add them all up using the integral. You add up all of the impulses from t1 all the way up to t2. Yeah, and this is called the impulse momentum theorem. It's just an integration of Newton's second law, really. Integral or integration of Newton's second law. Integration in time.